Harmonics generated by nonlinear loads can indeed cause problems on all three-phase power services. It's a common misconception that these issues are exclusive to Y systems. To understand why, let's delve into the nature of harmonics and how they interact with different three-phase configurations. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency of the power system. For instance, in a 60 Hz system, the second harmonic is 120 Hz, the third is 180 Hz, and so on. These harmonics are created by nonlinear loads. Nonlinear loads are devices or equipment that draw current in a non-sinusoidal manner. Common examples include variable frequency drives, electronic ballasts for lighting, switching power supplies found in computers and other electronic devices, and uninterruptible power supplies. The non-sinusoidal current drawn by these loads distorts the voltage waveform on the power system, creating harmonics. Now, let's consider how these harmonics propagate through a three-phase system. Three-phase power systems are used to distribute electrical power efficiently and reliably. There are two primary types of three-phase connections, Y and delta. In a Y-connected system, the three phases are connected to a common neutral point, forming a Y shape. The voltage between each phase and the neutral is called the phase voltage, while the voltage between any two phases is called the line voltage. In a delta-connected system, the three phases are connected in a closed loop, forming a triangle shape. There is no neutral point in a delta system. The voltage between any two phases is the line voltage, which is also equal to the phase voltage in a balanced system. The impact of harmonics can be observed in both Y and delta systems, but the specific manifestations and mitigation strategies may differ. In both types of systems, harmonics can lead to several problems. Firstly, increased current flow can occur. Harmonic currents add to the fundamental frequency current, increasing the overall current flowing through conductors. This can lead to overheating of conductors, transformers, and other electrical equipment, potentially reducing their lifespan and increasing the risk of failure. Secondly, voltage distortion can result. Harmonic currents flowing through the impedance of the power system create voltage drops at harmonic frequencies. This voltage distortion can affect the performance of sensitive electronic equipment, causing malfunctions, data errors, or premature failure. Thirdly, resonance can be triggered. Harmonic frequencies can sometimes coincide with the natural resonant frequencies of the power system. This resonance can amplify harmonic currents and voltages, leading to severe voltage distortion and equipment damage. Fourthly, neutral overloading can occur, particularly in Y systems. Triplet harmonics, which are odd multiples of the third harmonic, such as the third, ninth, and 15th harmonics, are additive in the neutral conductor of a three-phase Y system. This can result in excessive current flowing through the neutral conductor, even if the phase currents are balanced. This neutral current can cause overheating and potentially damage the neutral conductor and connected equipment. Now, let's examine how harmonics affect each type of three-phase system more specifically. In Y systems, the presence of a neutral conductor provides a path for triplet harmonic currents to flow. As mentioned earlier, these currents add arithmetically in the neutral, potentially leading to overloading. Moreover, voltage distortion caused by harmonics can affect the line to neutral voltages, which are the voltages seen by single-phase loads connected to the system. This can cause problems for sensitive electronic equipment that relies on a clean sinusoidal voltage waveform. In delta systems, there is no neutral conductor, so triplet harmonic currents cannot flow directly back to the source. Instead, these currents circulate within the delta loop. This circulating current can cause overheating of conductors and transformers within the delta system. Furthermore, harmonics can still cause voltage distortion in delta systems, affecting the performance of connected equipment. The absence of a neutral does not eliminate harmonic problems, it merely changes how they manifest. It is important to note that the severity of harmonic problems depends on several factors, including the magnitude and type of harmonic currents, the impedance of the power system, and the sensitivity of connected equipment. To mitigate harmonic problems, several strategies can be employed. Firstly, harmonic filters can be installed. Harmonic filters are designed to reduce the amplitude of specific harmonic frequencies. They typically consist of tuned circuits that provide a low impedance path for harmonic currents, diverting them away from the power system. Secondly, phase-shifting transformers can be used. Phase-shifting transformers can be used to cancel out certain harmonic frequencies. For example, a delta-Y transformer can be used to trap tripling harmonics within the delta winding. Thirdly, harmonic mitigation equipment can be implemented. Harmonic mitigation equipment can reduce the harmonic content generated by nonlinear loads. For instance, active harmonic filters can inject currents into the power system that are equal in magnitude but opposite in phase to the harmonic currents produced by the load. Fourthly, proper grounding practices should be followed. Proper grounding can help to minimize the effects of harmonic currents. A well-designed grounding system provides a low impedance path for harmonic currents to flow, reducing voltage distortion. Fifthly, selecting appropriate equipment is important. When selecting equipment, consider its harmonic characteristics. Choose equipment with low harmonic emissions or that incorporates harmonic mitigation features. Sixthly, regular monitoring and analysis is crucial. Regularly monitor and analyze the power system for harmonic distortion. This can help to identify potential problems and ensure that mitigation strategies are effective. Now let's consider some real-world examples of harmonic problems in three-phase systems. In a commercial building, a large number of computers and electronic devices can create significant harmonic distortion. This can lead to overheating of transformers, nuisance tripping of circuit breakers, and malfunctions of sensitive equipment such as medical imaging devices. In an industrial plant, variable frequency drives used to control motor speed can generate substantial harmonic currents. These currents can cause voltage distortion, overheating of conductors, and interference with communication systems. In a data center, uninterruptible power supplies used to provide backup power can be a significant source of harmonic distortion. This can affect the reliability of the data center's power system and potentially lead to data loss or system downtime. To accurately assess and address harmonic issues, several measurements and calculations are commonly used. Total harmonic distortion, or THD, is a common metric to measure the extent of harmonic distortion in a system. It represents the ratio of the root mean square value of the harmonic content to the root mean square value of the fundamental frequency component, expressed as a percentage. There are two common types, THD voltage and THD current. The formula for THD voltage is the square root of the sum of the squares of the harmonic voltages, divided by the fundamental voltage, then multiplied by 100%. The formula for THD current is the square root of the sum of the squares of the harmonic currents, divided by the fundamental current, then multiplied by 100%. IEEE Standard 519.1992 provides recommended limits for harmonic voltage and current distortion in power systems. These limits are designed to prevent harmonic problems from affecting the performance of connected equipment and the overall reliability of the power system. The standard specifies different limits for different voltage levels and system configurations. For example, for general power systems, the individual harmonic voltage distortion should not exceed 3%, and the total harmonic distortion should not exceed 5%. For current distortion, the limits vary depending on the size of the load relative to the size of the power system. In addition to THD, other metrics such as individual harmonic distortion and telephone interference factor are also used to assess harmonic problems. Individual harmonic distortion measures the amplitude of each individual harmonic frequency. Telephone interference factor measures the potential for harmonic currents to interfere with telephone communication systems. Harmonic analysis software is often used to simulate and analyze harmonic behavior in power systems. This software can help to identify potential harmonic problems, evaluate the effectiveness of mitigation strategies, and ensure that the power system meets applicable harmonic standards. The impact of harmonics can also depend on the transformer connections in the three-phase system. Delta-Y transformers are commonly used to block tripling harmonics from propagating from the load side to the source side. The delta winding provides a closed loop for tripling harmonic currents to circulate, preventing them from flowing into the source. Y-delta transformers, on the other hand, can allow tripling harmonics to flow from the source side to the load side. This can be a concern if the load is sensitive to harmonic distortion. Zigzag transformers are a special type of transformer that can be used to mitigate harmonic problems. Zigzag transformers have a unique winding configuration that allows them to cancel out trip and harmonic currents. They are often used in applications where harmonic distortion is a significant concern, such as data centers and industrial plants. It's also important to consider the impact of harmonics on power factor correction capacitors. Capacitors are often used to improve the power factor of electrical systems. However, capacitors can also be susceptible to harmonic currents, which can cause them to overheat and fail. To prevent this, harmonic filters are often installed in series with power factor correction capacitors. This helps to reduce the amount of harmonic current flowing through the capacitors, protecting them from damage. In summary, harmonic problems are not limited to Y systems, they can affect all three-phase power services. The specific manifestations and mitigation strategies may differ depending on the system configuration, but the underlying principles remain the same. Understanding the nature of harmonics and their impact on electrical systems is essential for ensuring the reliable and efficient operation of modern power systems.